Hey everyone, this is Daniel for Rock the JVM, and this video is far more beginner-friendly because we're going to talk about recursion not only as a programming tool, but rather as a thinking tool that will allow you to write, read, and understand code far more easily. If you're a senior developer, you might consider using this video as a teaching tool for the juniors in your team. Now, as is generally the case with videos on the Rock the JVM channel, I'm going to demonstrate the code examples in the Scala programming language, but the concepts that I'm going to talk about here will apply to pretty much any other programming language that you might want to write code in, including Kotlin, or hell, even Java, or JavaScript, or TypeScript, or pretty much everything in between. And I'm going to demonstrate these ideas with one classical computer science problem that seems very difficult when you're starting out, especially with functional programming or recursion, which is the idea of sorting lists. And I'm going to demonstrate multiple versions of sorting lists just for you to get an idea for how to think different algorithms in terms of recursion instead of do this, do that, algorithmic thinking. Now, for this video, in order to be able to write any code, I'm going to expect that you know at least a bit of syntax. And in Scala, for this particular example, I'm going to write my sorting methods as extension methods on the list type. So I'm going to use an extension clause. I'm using Scala 3, by the way. So extension A with a list as a list A, I'm going to define a bunch of methods. I'm going to define, for example, an insert sort that takes a comparison function as a function AA arrow int. And the comparison function AA arrow int says that if the int is less than 0, then the first element is so-called less than the second element. If the int returns 0, then these two elements are deemed equal, and it doesn't matter in which relative position they sit in the sorted list. And if the int is bigger than 0, then that means that the first element is so-called bigger than the other one. And that will give me back a list of A, which is the sorted version of the original list. So I'm going to leave this unimplemented for now. And I'm going to copy this to two other insert methods. So instead of insert sort, I'm going to use merge sort and quick sort. So these are some classical computer science algorithms that we learned very early in our training as software engineers or computer scientists. And we naturally tend to take quite a bit of time to implement these algorithms, especially merge sort and quick sort correctly in an algorithmic thinking. But with recursion, these things take very little time to write and also very little time to think. This video is more me talking rather than just writing code. For example, in insertion sort, the fundamental operation is to be able to insert an element into a sorted list. So the auxiliary method that I'm going to write inside is an insert that takes an element as an A, and the rest of this list as a list of A, and this returns list of A. Now, I'm going to leave this unimplemented, and the list of A that we are going to return is the addition of the first element into the rest of this list in the correct position. Okay, now one good way to get familiar with the concept of recursion is to put yourself in the situation where you cannot really think in terms of algorithms. For example, in this case, I'm using the list data structure in Scala, which is not the same as an array, which is mutable, and you can swap elements inside, and you can change the value of a particular element at a particular index. Whereas with lists, you cannot really do that. So naturally, you'll have to think in terms of recursion, which forces your brain to approach this code in a new way. So assume that this insert function worked correctly for some reason. So assume that this implementation worked nicely. How would you implement insert sort? Well, first of all, the expression that returns the sorted list is to say if the list is empty, or the list contains just one element, so list.tail is empty. And is empty and tail are two fundamental methods of the list data type. Then I'm going to return that same list. Otherwise, so the expression says that if the list is empty or the list tail is empty, I'm going to return the same list. Otherwise, I'm going to consider that the head is taken out of this list, the head being the first element of this list. I'm going to say insert with list head and the sorted version of the tail of this list. So I'm going to say list tail insert sort with the same comparison function as an argument. This is the entire implementation of insertion sort. Look at this expression. It's super compact and it's super descriptive of what it does. So if the list is empty or the list contains just one element by saying list tail is empty, I'm going to return the same list because there's nothing to sort. Otherwise, I'm just going to insert list head into whatever the insert sort returns. Considering that this insert sort method worked correctly, then this is the sorted version of the rest of this list, and all I have to do is insert the head into that sorted version and obtain the final sorted version. So ignoring the insert method for now, this is the entire insert sort algorithm. Recursion does most of the work. Now, recursion obviously is the ability of a function to call itself, but this is not just a mere programming trick. Here, in this particular expression, recursion describes what it means for a list to be sorted. And as for the insert method, it's also a single expression. For example, if the rest is empty, then all you have to do is just contain the element that you want to add. Otherwise, then you have to compare the element that you want to add with the first element of the rest of this list. So I'm going to say if the comp function applied to lm and rest head is less than 0, then that means the element that you want to add is smaller than everything else. So it has to sit first. So I'm going to have lm : rest. Otherwise, the rest's head, the first element of this list, is the smallest one. So it has to stay first. So rest head. And then I'm going to recursively insert the element into the tail of this one. So I'm going to say rest.tail, subject to the insert function. So insert with the element and rest.tail. So that is it. This is the entire algorithm for insert sort. In total, we have like 8 lines of code. And we can actually test this out. So I'm going to have a value, let's call this random list as I'm going to create 1,000 elements. I'm going to have 1 to 1,000 dot map, and for every element, I'm going to have random dot next int, and I'm going to have next int from 0 to 100,000 or 0 to 1 million, and then I'm going to say toList. So this is a list of 1,000 elements randomly generated from 0 to 1 million. And I'll need a comparison function. So I'm going to have val, let's call this natural comp, which is a function int arrow int. And I'm going to use one of the standard library functions. I'm going to say ordering of type int dot compare. So this is the function that I'm going to use. Essentially, this is the natural comparison of integers. You can also define your own. And I'm going to, let's call this sorted 1 as random list insert sort with this natural comp. I'm just going to print line sorted 1 dot, let's say, take 30, because I don't want to print the entire 1,000. Maybe let's just print the entire thing. Let's see what we got, and then we can clean this up. So let's just print this up. And look at that. We have a sorted list, which contains a bunch of elements, starting from 665 and increasingly up to 998,000, whatever. You can see and you can tell that this is a properly sorted list. And just to remind you, it took 8 lines of code. Okay, let's move on to merge sort. Merge sort is quite complicated when you implement it for the first time, but again, recursion makes it far easier. The important function of merge sort, just like it was the case for insert sort, is the ability to merge 2 sorted lists. So I'm going to have merge for half left, which is a list A, and half right, which is a list A. And I'm going to return a list A, which is the sorted merging of these two. So assuming that HL and HR are 2 sorted lists, I'm going to obtain a new list, which is the combination of these 2 in sorted order. Okay, now assume that this thing worked correctly. I'm going to implement it later. What's the implementation of merge sort? Well, it's pretty much the same thing. So if list is empty or list tail is empty, I'm going to return the same list. Otherwise, I will split the list in half. So I'm going to have val, let's call this split as list dot split at. I'm going to have list length divided by 2. And this split is going to be a tuple, list A and list A. And in Scala, you can actually destructure the tuple very easily, like you can in Python. So HL and HR. These things are not sorted yet, so I'm going to have to sort them. So HL sorted as HL.mergeSort with the same comparison function. And val HR sorted as HR.mergeSort with the same comparison function. And finally, I'm going to merge these two. So I'm going to say merge with HLS and HRS. So this is the entire implementation of merge sort. So ignoring the sanity check here, list is empty and list tail empty, I'm going to return the same list because there's nothing to sort. Otherwise, I'm just going to split the list in half. I'm going to recursively call merge sort on the first two halves. And assuming that this works correctly, I'm going to simply merge these two together by calling the merge function, and this will give me back a list which is correctly sorted in total. Okay. Now, what about the merge? Well, if either of these two lists is empty, then I'm going to return the other one. So for example, if HL is empty, I'm going to return the other one, so HR. Otherwise, if HR is empty, I'm going to return HL. Otherwise, neither of these two lists is empty, so I should be able to compare their heads. So if the comparison function applied to HL head and HR head is less than 0, so if the comparison function between these two heads is less than 0, then the first one's head is the smallest one. Therefore, it should stay the first in the result. So I'm going to say HL.head combined with. And what is going to sit after that? Well, I'm going to merge the rest of the HL because I've just taken its head, and then HR. So I'm going to say merge between HL tail. So I'm just going to skip the head because I've just placed it at the beginning, and then HR because from HR I haven't consumed anything yet. Otherwise, the other value should be placed first. So I'm going to say HR.head, and then merge between HL because I haven't consumed anything from this one yet, and HR tail. And this is the entire merge implementation. It's 4 lines of code, 2 of which are just sanity checks. So for the entire thing, we're looking at roughly 10 lines of code. And again, from the philosophical standpoint, the ability of a function to call itself, which we know as recursion, is also a way for us to describe what the code returns to us. And in this way, it's very easy for us to rely on the correctness of pieces of our code, even though we haven't written them yet. So if you remember, I'm just going to cut out the implementation. Remember, we started out with the merge function defined as question marks, so we had no idea how the merge function was supposed to work, and we still could write the merge sort implementation in a correct way just by looking at what the merge function returned to us and relying on that. So recursion and functional programming in general is a good way to free up some of your mental burden and focus on the task at hand and relying on the correctness of other pieces of your application or of your software. And that is true even in the implementation of the function itself. And this is where recursion is a particularly powerful tool, because assuming that your function worked correctly, you can also use the result of that in the implementation of the function itself. Now, if you're just starting out and functional programming or recursive approaches are quite hard for you to parse, if you talk to a senior developer, this is as clear as day. There's nothing in this code that could go wrong in terms of how the algorithm operates. Let's try one more with the quicksort, which is very easy to get wrong, very easy to get bugs if you are building it in an imperative way. But with recursion, it's super quick. I'm not even going to add any auxiliary functions because I'm going to implement it in one expression. So if the list is empty or list tail is empty, I'm going to return the same list just as before. Otherwise, the idea of quicksort is to isolate one item of the original list. We call that a pivot, and you can pick either one. I'm just going to pick the list's head. So I'm going to say pivot as the list head. And the idea is to be able to partition the list into 2 sublists. One list is, or list number 1, is elements smaller than the pivot, or smaller than equal. And list number 2 is made of elements that are bigger than or equal to the pivot. If you can do that, then you can sort them out. So sort list 1, then the pivot, then sort with list 2. And we can actually write this exact thing in the code. So I'm going to say val, let's call this split, as list.tail. So I'm going to skip the list head. So all the rest of the elements. So list.tail, and there's a function called partition. You can also define that yourself and traverse the list and just store the elements that are smaller or equal to the pivot. But I'm just going to use this method because it runs well in the standard library. So I'm going to pass a function, x, and the function that I'm going to pass in here is to say elements are smaller than the pivot. So I'm going to use the comparison function between x and pivot. And I'm going to make this function return less than 0, meaning that x is quote-unquote less than the pivot. So this split is going to be a tuple, list A with the elements that satisfy this predicate, so the smaller elements than the pivot, and the elements that do not satisfy the pivot, which are the elements that are greater than or equal. So what I'm going to do here is I'm going to call quicksort on list number 1. So I'm just going to call this list number 1, or simply smaller and bigger. Just going to destructure the tuple, and I'm going to say smaller dot quicksort with the comparison function, and then so I'm going to concatenate the list pivot, and then bigger dot quicksort on the same comparison function. So the way that I have to do that is to use the concatenation, which is ++, and the pivot and sort list number 2 has to be written like this because otherwise the compiler won't compile my code. Okay, so smaller quicksort comp plus this other list, which is made of the pivot and the elements that are at least as big. That is it. This is the entire quicksort implementation. This is essentially 5 lines of code. And we can also test this out. So let's have more sorted lists. So sorted 1, sorted 2, sorted 3. I'm going to use merge sort and quick sort. And print line sorted 1, which is going to be my first list, and I'm going to also print line the fact that sorted 1, sorted 2, and sorted 3 are the same list. So I'm going to say sorted 1 is equal to sorted 2, and sorted 2 is equal to sorted 3, just to testify that these algorithms work in the same way and give us back a similarly sorted list. And we have the sorted list here, and we return true. Notice that all of these 3 sorting algorithms took from line number 9 to line number 41. So in 40 lines of code, we implemented 3 different sorting algorithms for lists, which tells you something about recursion. Recursion leads you to some very, very compact code that's easy to read and understand, especially if you've taken some time to practice this. If you practice even half a dozen recursion-based problems, this will become far more easy for you to read and understand, and also far more natural for you to think and approach your code. Now, recursion also may come with other criticisms, especially in terms of runtime, because every recursive call will occupy a little memory zone in the stack. And if you have many, many recursive calls, you may lead to Stack Overflow errors. For example, if this list is very big, every function in there is going to give us a Stack Overflow error. But this problem is much more easy to overcome with a technique called tail recursion, which we'll talk about another time. I practiced this in my Scala and functional programming interview practice course, in which we test different data structures and algorithms and lead code style problems with this particular technique that will allow you to avoid Stack Overflow issues. But we're going to talk about this in another video. For now, just enjoy the benefits of recursion in the ability to read, understand, and look at very compact code with provable correctness. So I hope you enjoyed this video and found it valuable. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this. And if you want, you can check out my website at rockthejvm.com, in which I have literally hundreds of hours of pretty much everything in the Scala and Kotlin and Flink and Apache Spark ecosystems. If you want, I'm going to leave a link in the description. Until next time, folks, this is Daniel signing off.